Hello everyone, and welcome to the online session for the heat transfer. Today I am going to talk about the radiation heat transfer. Up to now we have considered two different types of the heat transfer. We discussed about the conduction heat transfer and convection heat transfer during the previous sessions. Today we are going to start to consider the heat transfer by radiation. What today actually you should learn after today's session, you will see how is the mechanism of the energy transfer by radiation. You will understand that. And also we will see how is the properties of substances effective on the radiation heat transfer according to different laws like Kirchhoff, Wiens, and Stefan Boltzmann law, which I think you already know about that. And we will see what is black body, and we will define the radiation function, which is according to this black body concept. And we will see some example of this radiation heat transfer in everyday life and in different aspects of our life. First, let's see what is actually this radiation heat transfer. As you may have had experience about that, any hot object will have some kind of the thermal energy. As you can see in this figure, for sure all of you have had this experience. If you stay near a source of the thermal energy like a fire, you can feel some kind of that thermal energy or heat. This is due to this radiation heat transfer. Or in a better example, a hot object in a vacuum chamber will lose heat by radiation only. In other words, when we have a hot object in this vacuum chamber, we don't have any conduction and convection heat transfer from that hot object to the surrounding by convection, because we don't have any media around that or any liquid for the convection and any media to have a conduction heat transfer. So all of the heat loss in that body to the surrounding is due to the radiation heat transfer. And also you can see in these figures the differences between these type of the heat transfer with the convection and conduction. As you can see here, the temperature of the fire is about 900 degrees Celsius. Temperature of the person here is 30 degrees Celsius. And this heat transfer is happen through the air, and the thermal energy is reached to the body of this person. Even the temperature of the media between those two is less than the temperature of the receiving object. So unlike conduction and convection, heat transfer by radiation can occur between two bodies even when they are separated by a medium colder than both. This is the difference between the radiation and convection or conduction. So radiation differs from the conduction and convection because it does not require the presence of material or medium to take place. In other words, if there is a vacuum, still we have this radiation heat transfer. And also the radiation transfer occurs in solids as well as liquid and gases, and we will see how it is happening. But before we further go through this radiation concept and calculate how is it happening between two different objects, or in a better word, between two different surfaces, we should know what is exactly this the source of this radiation or thermal energy. As you know, the charge of changing electric currents give rise to electric and magnetic fields. And these rapidly moving fields, we call them electromagnetic waves or electromagnetic radiation, which you know about that. You can see different application of this radiation around us, like our TV, phone, and also even the light. All of them are the electromagnetic waves, and these waves have energy. This energy comes from their electronic configurations of the atom or their molecules. And these electromagnetic, like any other waves, for example, the mechanical waves you can see in the, for example, a lake or other kind of the waves, can transport energy. Actually, the radiation is transferring this electromagnetic energy between different bodies or objects. And these electromagnetic wave energy or electromagnetic waves can be characterized by the frequency, you can see here, and the wavelengths. These two parameters are important when you are dealing with the waves. Here we have electromagnetic waves. These two properties are related to each other by this equation, lambda equal to c divided by v. Lambda equal to c divided by no. As you can see here, lambda is the wavelength of the wave, which is important. Later we will have different application for this lambda. In it will play a significant role in our calculations, so it's better to understand it better. Lambda is equal to c divided by no. C also can be calculated by this equation, c equal to c0 divided by n. C is the speed of the propagation of a wave in that medium. So as you can see here, the frequency or wavelength should be defined according to the medium which that wave is going through that. And also C0 in this equation to calculate the C is the speed of light. Actually, speed of light in a vacuum, it is 2.9979 times 10 power 8 meter per second. And n is in this equation to calculate the speed of propagation is the index of refraction of that medium, which is a characteristic of the medium which these electromagnetic waves is going through that. And this n or index of refraction is 1 for the this n is 1 for the most of the gases, n is 1.5 for glass, and it is equal to 1.33 for water. And as you can see here, this n is only for the transparent material, because these electromagnetic waves usually we just consider them when they are going through the transparent material, and in most of the cases we calculate for this type of the material. And one more interesting thing about the electromagnetic radiation is that, however we call them waves, they have such kind of the characteristic which this energy or this energy which is transferred by the electromagnetic waves is packed into the some discrete packets, which we call them photons or quanta. And to be honest, it is very complicated phenomenon, this characteristic of the electromagnetic waves, because they are in the same time they are waves and also they are some kind of these packs. So it is interesting to know that the energy by this wave is transferred, which is packed in different packets, which we call that photons. And each photons of frequency v, which we frequency of v, is considered to have an energy of this much, E equal to h no or equal to hc divided by lambda, which is the energy of photon, and it is inversely proportional to its wavelength. So the waves which short with the shorter wavelengths or shorter lambda will have higher energy. This is important. We will see how it is effective on the energy of the different type of the electromagnetic waves. And the h is a Planck's constant, which is equal to 6.6 something times 10 power negative 34 joule per joule second. This is a constant to calculate the energy of any photon in electromagnetic waves with lambda wavelengths. What you can see here in the right side of the slide is the electromagnetic wave spectrum. It is a very important figure to understand which type of the electromagnetic wave is our wave, which we are interested to know more about that. As you know, as you may know about that, the sunlight or light or visible light, actually, it's only a portion of this electromagnetic wave spectrum. As you can see here, we have the waves with the wavelengths from 10 power negative 9, very short wavelengths, to long, very long waves, which is in 10 power 10 micrometer. So from 10 power negative 9 micrometer to 10 power 10 micrometer. This is the common spectrum of the electromagnetic wave, and you can see in different wavelengths we have different kind of the waves, actually, or different ray, I can say. And you can see here, this is visible spectrum or visible waves. You can see electromagnetic wave. You can see how much is its range is small, and you can see X-ray. This is toward the shorter waves, higher energy of the wave. You can see here visible shorter wave, ultraviolet, and shorter X-rays, gamma rays, and cosmic rays, very short wavelengths. And you can see higher wavelengths to go to the microwaves, radio and TV waves, and electrical power waves, and etc. So what we are interested is about this range, which is thermal radiation, some part of the ultraviolet, invisible, and infrared, as you can see here. So The type of electromagnetic radiation that is pertinent to heat transfer is thermal radiation. This part emitted as a result of energy transition of molecules, atoms, and electrons of a substance. Temperature is a measure of the strength of these activities at the microscopic level, and the rate of thermal radiation emission increases with increasing temperature. This thermal radiation is continuously emitted by all matter whose temperature is above absolute zero. We introduced this thermal radiation because of the movement or energy transition of molecules, atoms, and electrons. So any substance which has this kind of molecules, atoms, and electrons which can move and emit this thermal radiation will produce this thermal radiation or some kind of energy. But when they reach this absolute zero, means negative or absolute zero or the 0 Kelvin, it means that all of the molecules and atoms are fixed and they cannot produce this energy. So in our daily life, all of the objects we can see around us has some kind of this molecule that can produce this thermal radiation. So everything around us constantly emits thermal radiation, and we can feel that. For example, if you just stay at a room, you can feel that the temperature of the inside of the room or is different from the outside. One reason is this thermal radiation comes from different objects in the house. You can see also the difference in the temperature of the house when more objects are in the room compared to the empty place. And I told you about the light. Light is only visible portion of the electromagnetic spectrum that lies between 0.4 and 0.76 micrometer. Let's go back. You can see here visible this part, 0.4 to 0.76 micrometer of this electromagnetic spectrum goes for the light. And this light, which we can see, consists of different colors, but the wavelengths also for the different color is different. What we can see now is due to the this fact that we can see the visible light, which is we can see it is white or without color, but you can see here this visible light, this visible or this visible portion of electromagnetic spectrum or the light also contain different type of or different colors. When the wavelength is 0.4 to 0.44 micrometer, it will be violet. If its wavelength is 0.44 or 0.49 micrometer, it will be blue, and so on. So you can see from violet to red, this range is increasing. And the radiation emitted by bodies at room temperature falls into the infrared region of the spectrum, which extends from 0.76 to 100 micrometer. The infrared actually is the longer wavelengths you can see in the spectrum. This is infrared. It is out of the visible range of the electromagnetic waves, and you can see it consists of 0.75 almost to 10 power 2 or 100 micrometer. And many of the objects around us are emitting or emitting this kind of the radiation. And ultraviolet radiation includes the low wavelengths end of the thermal radiation spectrum, and it lies between the wavelengths on 1.01 and 0.40 micrometer. Ultraviolet, as you can see here, visible is between these two, infrared and ultraviolet. Ultraviolet shorter and more energy, with more energy waves compared to visible. Infrared, lower energy compared to the visible waves. So ultraviolet rays are to be avoided, since they as I told you, their energy is higher than the light or visible magnetic electromagnetic waves, and they can be used. They are useful, and also they have some disadvantages. As you may heard, we can use these ultraviolet rays to kill microorganisms, but they can also cause some serious damage to our bodies. They can kill also or change the microorganisms in our body, change the our cells, and cause some skin cancer. So this ultraviolet, we will see later how much, and the sunlight, actually what we call that sunlight, it consists of different kind of magnetic electromagnetic waves. One of them is this ultraviolet, and you will see how much of that is this ultraviolet and how it is effective. As you can see here, about 12% of solar radiation is this ultraviolet, or it is in this ultraviolet range. So it may be very dangerous for our body, but the ozone or O3 layer in the atmosphere can act as a protective blanket and absorb this ultraviolet radiation, and also actually it protects us against the ultraviolet radiation by the sun. And we have some summary of what I told you in this slide. The body that emits some radiation in the visible range is called the light source. So if any object produces light, we call that light source, or it is producing electromagnetic waves, which we can see that. And the primary source for this light is sun, which we can see its light easily. The electromagnetic radiation emitted by the sun is also known as solar radiation, and it is nearly all of it, and also nearly all of it falls into the wavelengths of 0.3 to 3 micrometer. 0.3, if we see here, almost here, visible, some of that, and all some ultraviolet to 3 micrometer. So it is in this range, the solar radiation, half of that actually. And half of this solar radiation is light, or it falls into the visible range, as you can see here. This is visible range, this is the solar radiation from 0.3 to 3, most here. So half of that is in visible range. And the other parts, as I told you, it's the ultraviolet and infrared, which 12% is actually ultraviolet. So half of that visible range, 12% ultraviolet, and almost 38% will go for the infrared radiation. And we use this concept, this radiation or thermal radiation, in some daily application. As you can see here, this is a microwave oven. Food is heated or cooked in a microwave oven by absorbing the electromagnetic radiation energy, which is generated by a magnetron of the oven. This is one real application of this thermal radiation. And as I told you, the source of this thermal radiation is the movement of these electron atoms and molecules, which are in the solid, liquid, or gases, and their temperature is higher than the absolute zero. This will cause production of this thermal radiation. And one more interesting thing about this is how it is happening from the surface, or it is a surface phenomenon, or it is produced in the entire volume of the object. Actually, this radiation is a volumetric phenomenon. In other words, the molecules are spreading in all of the bodies, so they are produced in all volume of the bodies or objects. But for the opaque solids, which the molecule inside the object cannot radiate or emit this energy to the outside, we just consider this thermal radiation as a surface phenomenon. So for the solid like this, we only consider the radiation from their surface, for opaque solid actually. Before we introduce the calculation for the this thermal radiation, we should know some assumption and some criteria actually. As I told you, different bodies may emit different amount of radiation per unit surface area. Similar to other method of the heat transfer, the object with different surface area may produce different amount of radiation. And this depends on some characteristic of the object. But the object with the maximum amount of radiation for a specific temperature of its surface is called the black body. In other words, black body is the object which its radiation from its surface at a specific temperature is maximum. It is an assumption and it is imaginary object. We call that black body. And we should define this black body to have idealized body to compare the radiation or this thermal radiation by this idealized. So in our consideration, we will always compare the radiation from different material. We'll compare that with the radiation of this black body. And also we should know that the black body is a perfect emitter and absorber of radiation. As I told you, maximum emits, so also it will absorb, its absorption is also maximum. And also a black body absorbs all incident radiation regardless of wavelength and direction. We will see why it is important, but we should assume that a black body will absorb all these incident radiation regardless of wavelength and direction. We will see that the wavelength and direction is effective on the amount of radiation for the normal material, but the black body, we can imagine that it can absorb all of these incident radiation. And also we have another definition. Later we will see that in more detail, but briefly I can introduce here that a black body is said to be a diffuse emitter. Diffuse emitter means it emits radiation energy uniformly in all directions, as you can see here. In real body we will have something like this. As you can see here, the radiation in different direction will be different, but we can imagine for a black body that the emission or the radiation from the surface of a black body is something like this. It is uniformly emitting. Then we can calculate the radiation energy emitted by a black body, idealized body actually. So the radiation energy, or EB, with object with temperature of T will be equal to sigma T power 4. We had this equation in a previous chapter as well, sigma T4 if you remember, but here we have a new definition for that. This is radiation energy actually. EB at temperature of T equal to sigma times that temperature power 4. This sigma is Stefan Boltzmann constant, and it is equal to 5.67 times 10 power negative 8 watt per meter square times K power 4. So this is black body emissive power. Now let's see how we can find this radiation energy for other object as well. We have a definition for spectral black body emissive power. This spectral black body emissive power actually is the amount of radiation energy which is emitted by black body at a thermodynamic temperature T per unit time, per unit surface area, and per unit wavelength about the wavelength lambda, as you can see here. This is a spectral black body emissive power. The difference between these and previous equation is introduction of this lambda. As you can see here, lambda or wavelength of the that kind of electromagnetic wave is effective on the energy of this radiation energy. So here we have added this lambda, which is the wavelength of the electromagnetic wave, which we are interested to know its radiation energy, like what we had here, but here for different lambda or wavelengths. It is equal to C1 divided by lambda power 4 exponential of C2 divided by lambda t minus 1. C1 and C2 are constants and can be calculated by this equation. C1 equal to 2 pi h C0 power 2, and C2 is equal to this much. And C0 we have introduced in a previous slide how much is it, but usually we can just put C1 and C2 in this equation to calculate this spectral blackbody emissive power. And K here for C2, it's also a Boltzmann constant. We can just substitute in this equation to calculate C2. And one more thing about our assumption about this black body. Most of the objects we are dealing with are such a kind of this cavity, which for enough large isothermal cavity temperature at a temperature of T, with a small opening of area like what we have here, it can be closely resembled as a black body of surface area at same temperature. So in other words, this small opening of area is not that much effective on the total power or thermal energy of these kind of the black bodies. Then if we want to draw a graph to know the relationship between this spectral power or spectral black body emissive power A B lambda with the wavelengths of the electromagnetic waves for different temperature, as you can see here, 100 Kelvin, 300 Kelvin, will be something like this. And as you can see here, these by increasing of the wavelengths for waves, the power, this radiation power is initially increased, then it reaches a peak, and finally it will decrease. So the emissive power with for different wavelengths in different temperature is something like it. As you can see here, the pattern is similar for different temperature, but when the temperature of the object is higher, its peak or its emissive power will be higher, or its maximum emissive power will be higher. And this maximum happens at the when the lambda times t, or the wavelengths of the wave times temperature of the object or surface of the object be equal to this much, 2897 degree micromet times Kelvin. As you can see here, if you multiply the temperature of these, it's 100 Kelvin times to the its wavelengths for the maximum value of each one of them, we will find this value. So the wavelengths at which the peak occurs for a specified temperature is given by this equation, which we call that Wien's displacement law. By this veins displacement law, we can understand it in which temperature and wavelengths actually by knowing the temperature we can find the lambda. For lambda we can find the temperature. The maximum emissive power can be reached. And these observations are also listed here. The emitted radiation is a continuous function of wavelength. You can see here it is a continuous function. And at any specified temperature, it increases with wavelengths, reaches a peak, and then decreases with increasing wavelengths, like what you can see here. Increase, peak reach, and reached peak, and again it's fell down again. And at any wavelength, the amount of emitted radiation increases with increase of the temperature. You can see here this is in the direction of the temperature. And as the temperature increases, the curve shifted to the left, to the shorter region. Consequently, a larger fraction of the radiation is emitted at shorter wavelengths at higher temperature. In other words, with higher temperature, what I said or I read there, it is this phenomenon. As you can see, these curves, you know, the shape of the curve is similar, only their size is different. It is shifted for higher temperature to the left side, which means the shorter wavelengths or higher energy. So higher temperature will have higher this radiation energy or this power energy, emissive power actually. And this dashed line is also maximum power according to Wien's displacement. You can see for different temperature and different wavelengths. And the radiation emitted by the sun, which is considered to be a black body with temperature of 5780 Kelvin or roughly 5800 Kelvin, reached its peak in the visible region of the spectrum. Therefore, the sun is the tune with our eyes. As you can see here, this one, the biggest one is or the highest temperature is for the sun, and you can see its maximum is fell to the visible light region, as you can see here. So because of that, we can see the sunlight. If it fell or fall to the other region of these wavelengths, with this temperature we cannot see the sun actually. It's interesting. And on the other hand, the surface with the temperature lower than 800 Kelvin emit almost entirely in the infrared region and thus are not visible to the eye unless they reflect light coming from other sources. It says this part, this is 1000 Kelvin. You can see still in some part of the wavelengths we can see the object with this temperature. They can produce some kind of light actually, but if the temperature is less than 800, it doesn't fall into this region, which is the visible light region. So we cannot see the object. We cannot see any radiation from the object with the temperature less than 800 degree Kelvin. It is also interesting, and you can know why you can see the object when its temperature is increasing in some at some temperature you cannot see any radiation from its surface. Suddenly after temperature, which can see here it is 800 degree Kelvin, you can see the radiation from its surface. So this is what we can bring out from this graph, the relationship between the variation of black body emissive power with the wavelengths for several temperatures. And this this radiation energy or black body radiation energy also can be calculated by the graph, as you can see here, the graph of radiation energy and the radiation energy of the black body and wavelengths of the electromagnetic or radiation energy. Actually, we can also calculate this energy or radiation energy by this graph. As you may know, the area under this curve will give us this black body radiation energy, or EBT, which we have already introduced you. This radiation energy which is emitted from black body we can calculate by this equation. Here we introduce a new method to calculate this radiation energy of the black body, which is the area under the curve for a given temperature, and in different wavelengths. And as you may know from the mathematics, we can use this integration to calculate the area under this curve for lambda, d lambda from 0 to infinity. And that spectral this spectral black body emissive power will have another visible effect, which you can see in this figure. The incident light, as I told you in previous slides, constituent from different wavelengths, which each range of these wavelengths is related to one type of the color or one color. A surface which can reflect and absorb some kind of this some part of this radiation energy. If it absorbed the thermal energy of any of these color or wavelength, actually we cannot see the radiation from that surface for that color. But if it reflects that wavelength which is related to a color, we can see that color, like you can see here. This is incident light, which contains this color: red, yellow, green, blue. Yellow, green, blue is absorbed. We don't have any reflection for that, and we have reflection for red color. So we can only see red color for that object, actually. Okay, up to here I've introduced you how to calculate the radiation energy for black body for whole range of the lambda or wavelengths or electromagnetic waves, actually. But sometimes we are only interested to see how much is the radiation energy for some part of the wavelength or spectrum of the waves. Actually, I have introduced you in this slide the spectrum, the electromagnetic wave spectrum, as you can see here. That equation which I have introduced here is the radiation energy for whole range of the electromagnetic wave spectrum. Now we are interested actually to know how much is the radiation energy for specified wavelength. For example, how much is the radiation energy comes from the ultraviolet, how much comes from the visible light, for example. So we can use this equation. This is radiation energy which is emitted by the wave, which its wavelength is lambda. This equation, and as I told you in previous slide, it will be under the curve of the radiation energy lambda from 0 to that wavelength. By knowing these, we can define a new concept which we call that black body radiation function, or F lambda, which is the fraction of radiation emitted from a black body at a temperature of T in the wavelength band from lambda equal to 0 to lambda. This is black body radiation function of lambda, or in other words, we can write this F lambda at temperature of T, or black body radiation function at temperature of T equal to integration from 0 to lambda radiation energy of lambda for the waves with the wavelength of lambda and temperature T. The lambda, actually this is this part divided by sigma T power 4. This is the total radiation energy for whole spectrum of the electromagnetic waves. And this equation can also be written like this, which is very useful equation to calculate the radiation energy for the band of the waves, which from wavelengths of lambda 1 to lambda 2, as you can see here. And so this fraction of the radiation energy is equal to radiation radiation function for wavelengths of lambda 2 at temperature T minus radiation fraction function for waves with wavelengths of lambda 1 at temperature of T. As you can see here, it means this part of the radiation energy and lambda graph. Usually, to calculate the amount of the radiation energy for a wave, we can use this radiation function or black body radiation function. And the value for this function for different wavelengths and temperature can be found from different table. As you can see here, this table is showing the black body radiation function, or F lambda, as you can see here, for different temperature multiplied by lambda. So for a lambda and temperature, we can have these black body radiation function actually. Then if we know the wavelengths and temperature, if we know the temperature of the surface and also or an object, and we know the wavelength, then we can have this F lambda or radiation function or black body radiation function. Then we can calculate its radiation energy. Let's see it in a example how we can calculate the radiation energy of an object with specified temperature for different wavelengths in an example. Okay, now in this example we are going to see how to use that concept, that black body radiation function, to see how much of the light source is visible source actually. So for charge coupled devices or for charge coupled device image sensors that are common in modern digital cameras, like your phones. It is not actually your phones, but in this example you will understand why when you are capturing different image with your phone, the light source, the amount of light or the light near the object you are going to take a photo is effective on the quality of the photo. As it is mentioned here, these image sensors, which are already implemented in the camera, actually, if you see those cameras, CCD cameras, they are working and they are dependent on the quality of the light source. And with different light source, they with different spectral distribution, they will produce photos with different quality. Daylight and incandescent light may be approximated as a black body at the effective surface temperature. As I told you before, temperature of the sun is 5800 Kelvin, and the temperature of this kind of the light, incandescent light, can be imagined to be to 2800 Kelvin. So we should determine how much or the fraction of radiation emitted within the visible spectrum wavelengths from 0.4 micrometer, which is a wavelength for the violet color, to 0.76 micrometer, which is wavelength for red color, for each of the lighting sources. So we should calculate how much is the fraction of the visible band in this spectrum of the magnetic electromagnetic waves of these two different sources. Because this visible light actually is effective on the quality of the camera. Okay, let's see how much of the electromagnetic wave which is produced by these two sources is visible waves. So first we should assume that these two sources of the radiation energy, sun and incandescent light filament, behave like black bodies. Then we can use the concept related to this black body assumption. As it is mentioned in the question, the visible range of the electromagnetic spectrum extends from lambda lambda 1 equal to 0.40 micrometer and lambda 2 equal to 0.76 micrometer, which is mentioned here. So we have lambda 1 and lambda 2, and we have temperature for the sun, which is 5800 Kelvin. So first we should calculate this function. If we calculate this function for the different lambda times the given temperature, which is 5800, for example, here, then we can have this F lambda or black body radiation function. By knowing this, we can use this equation. we can use this equation to calculate the fraction or radiation use this radiation function to calculate the fraction of radiation emitted in that range of the lambda, which is visible range. So we know the lambda 1, we know lambda 2, which is mentioned in the question, we know the temperature. So lambda 1 T will be equal to 2320 micrometer time Kelvin, and lambda 2 also, which is 0.76 micrometer times its temperature for the sun, which is 5800 Kelvin. Then we can calculate this. So we have F lambda 1 for daylight, F lambda 2 for the daylight as well. By knowing this information, which is lambda 1 T or lambda T, 2320, 2220, it's almost here between 0.1, 0.10 and 0.14. By interpolation, we can find the value of this. As I told you before, there is continuous or relationship between these two values, so you can use interpolation to find the value between these two. Lambda T is, we have the black body radiation function for 2200 and 2400 of lambda T. So for 2300 something, it will be between 0.10 and 0.14. So you can see here it is 0.12. By interpolation we can find this. And for lambda 2 T, which is 4400, okay, 4400, almost here, it should be almost same to this 0.54. Yes, it is 0.55. So we have this function for that. Then we can calculate the fraction of visible radiation. As I told you, this lambda 1, lambda 2 is their range or band of the visible radiation. So we can calculate that F lambda 1 minus F lambda 2 equal to F lambda 1, this is for daylight, minus F lambda 2 for daylight. We have already found them from the table. Then it will be equal to this much, 0.42 almost, or if we multiply by 100, it will be 42.6%. So the fraction of the visible radiation emitted by the sun will be 42%. In other words, 42% of the sun radiation is in visible range. Then we will calculate this with the same procedure. We can calculate the this visible or the fraction of visible radiation for the incandescent light bulb, which its temperature is lower, is 2800 for same lambda 1 and lambda 2, similar to the for the sun, which is for the range of the visible wavelength. We can find this lambda 1 T, which is 1120, for example. It is near this, and you can see it between these two. We can find that for F lambda 1 and the temperature of the 2800 actually. And also we can calculate for the lambda 2T, is rank, this should be 2800. So lambda 2T for this one, let me just change it, 2800. So lambda 2T for the temperature of the light bulb, and the upper bound of the wavelengths range will be this much. From the table 2100 will be almost here between the 0.06, 0.1, it is 0.08. Then by writing the equation for that, we can find the fraction, and as you can see here, almost 8.7% of the radiation energy from the light is visible. So only less than 10% of the light will be the visible for the light bulb. Actually, for incandescent light bulb, only 10% of that will produce light. So as you can see here, 42% and less than 10%, nearly 50% of the sunlight is visible light. So it is a very good source of the light for capturing high quality photos. And less than 10% of these kind of the bulbs, which does not provide enough light source to capture high quality photos. So this kind of the light source, actually incandescent light bulb, now are substituted by LEDs or fluorescent light bulbs, which are more efficient, and their the fraction of the visible radiation is much higher compared to these incandescent light bulb. So you can see in this example how you can calculate the radiation energy from the or fraction of radiation energy for each band or range of the wavelengths in different temperature.